Okay, great. So once again, welcome to the Compass Lectures. This is the first lecture of the semester. I would like to introduce our first speaker of the semester, Itai Bloch. He started his college degree through a program called Future Scientists at the age of 13 in Tel Aviv University in Israel. He was fascinated by particle physics research, and as these things go, one thing led to another, and he officially started his PhD at 18, wow, at Tel Aviv University. After earning his PhD, he moved to Berkeley last year to start his postdoc. His main area of research is dark matter, but he does both theory and experiment. And in his free time, he enjoys reading fantasy and sci-fi, as well as writing and doing aerial acrobatics in the circus. That's awesome. Let's give a warm welcome to our speaker, Itai.
Thank you, Donnie. Admittedly, I thought that the short bio would be written somewhere, which would have been less awkward than hearing it in front of me. But thank you. So thank you very much for inviting me to give this talk, opening it. I'm very sorry for the virtual, non-virtual thing. I just recovered from COVID. I'm first day out of isolation, but I still cough a bit, so I decided to take the safe way. I'm going to tell you about what the existence of humans teaches us about the expansion of the universe and its final fate, though admittedly, I did write this title before I actually made the slide, so the balance between how much I talk about each different thing is different, and I also prefer my more adventurous title, which is How and Why the Universe Must Be Destroyed. Though I suspect that if I open with this title, I don't get to speak about particle physics and I'm put somewhere else. Let's put it that way. I was told I should probably start with an introduction. Some of it has already been taken by the bio, but I will say I started with my undergrad, and through it, in the middle, I started research in optical fibers in the Faculty of Engineering through the program through which I started the whole thing. And sorry, and that research was very nice, but after 1 year of research, I decided it wasn't really what I want to do with my life. So I asked to be placed in another program, and I was introduced to particle physics research. And with a big thank you to my previous advisor, Tomer Valansky, that piece of research that was supposed to be 1 year later became a PhD because I was so into it, and it was very much reciprocative of, letting me research more and more deeply. So I really do strongly recommend trying to test the waters when you're in your undergrad and seeing what kinds of research interest you. Like I said, I started with this thing in engineering and it ended up not fitting me. And then the thing in particle physics was so interesting that it ended up becoming a PhD. So I really think that it's really useful to try to start these things early on before you need to commit for your PhD or your master's, so you have more freedom. Now, my main research is dark matter detection, where I do both theory and experiment. I have both an experiment back where I did my PhD, as well as one on the Berkeley campus. But I also do some machine learning. Originally, I was just interested in the thing, so we did something unrelated to particle physics, and now we're working on integrating that into our research. And I also do a touch of quantum information. And I think what's really nice about the field I'm in, which is called particle physics phenomenology, is that there really is a lot of freedom and people do very, very different things. And you can kind of do things that are really kind of outside any reasonable definition of the field, and people won't raise too much of an eyebrow as long as you have in mind kind of, how this relates to the other things or you do. And I am happy to talk more about that afterwards. I also put my email initially, but I'm sure there are other ways to contact me in the universe, like probably on the website of like Berkeley Physics or something. So today I'm not going to talk about dark matter detection. I'm going to talk about cosmology, which is another thing I do. Though admittedly this research is a bit old, I'm currently working on continuations of this work. And I do find it to be very interesting because it talks about some people and it also, a lot of the things that are there are somewhat philosophical, though obviously are well entrenched in math and computations that are very fun to do, and most of them I will spare from you. So at 1915, this guy gave us general relativity. And in 1917, he tried to add something called the cosmological constant to make a static universe. And later, he would call this his biggest blunder, this attempt to make the universe static, basically. And we're going to talk about what this cosmological constant is and the staticness or expansion of the universe, or even contraction of the universe. And that's going to be the main thing we're going to talk about, basically. And the basic problem we are going to try to address is indeed called the cosmological constant problem. And obviously, I'm going to explain what that means. And of course, by the way, if you have questions, this talk, when I timed myself, was around 35 minutes, and we have 50 minutes. So there really is time for questions. We can always end a bit early. It's fine. So what I told you until now was history, which is not the main takeaway from the talk, because it's way too long to describe everything that happened. It's also not my expertise. The main takeaway of the talk, and I'm going to expand on exactly the details of this thing, is that if you have energy density in the universe, that causes the expansion of the universe. And exactly what are the ingredients of this energy density and what we think they should be and what they could be, that is the main thing we're going to discuss when we tackle this problem, which I call the cosmological constant problem. So an energy density over large distances is going to cause the universe to expand according to general relativity. And if you want to build our own universe, the list of ingredients, the three sources of energy density that we have is around 25% of it is dark matter, which is a very interesting subject for a completely different talk, so we're not going to talk about it. Around 5% is us, regular matter, i.e. protons, electrons, hydrogen gas, all the shebang, everything we know and love. And most of the energy of the universe is the energy of the vacuum or dark energy. And that's the main thing we're going to talk about. There is also a smidge of neutrinos and some small fraction of radiation, but they're really, really irrelevant for us. So we're not going to mention them at all. So most of the universe is this energy of the vacuum or dark energy. And as I will mention in a second, also cosmological constant. They are all basically the same thing, kind of. And that's what we're going to discuss. So throughout the talk, we'll have a bunch of illustrations that may or may not be directly related to what I'm talking about, because I found out that AI can draw things very nicely, and I have integrated that into the talk. So that is what AI gives you if you prompt it with dark energy. It's not really related. It's more looks like a black hole, but never mind that, because it's really pretty. So to understand what is the cosmological constant, we need to discuss what is the quantum vacuum. What is this thing that I mentioned is dark energy. It's all the same thing. So in quantum field theory, we have this prediction that particles and antiparticles are always created and destroyed. It's always going on. And these can be many, many different particles. It can be photons, it can be electrons, it can be anything. And this gives the nothingness, the thing where there's no other particle or radiation, some fixed average energy. Okay, so even if I take out all the particles, all of the light, all of the air, everything, there would still be some fixed energy in some box of space. And this box of space, this energy is what we call dark energy. And the density of this thing, i.e. how much dark energy I have in every given volume, that is what we call the cosmological constant. So indeed, these terms, dark energy and cosmological constant, are believed to be basically identical. And and they are the dark energy is just kind of the quantity, while the cosmological constant is the density of the thing. And another way to understand this object is basically kind of the absolute reference for potential energies. You may have heard during your high school years or whatever. Sorry, you may have heard that basically, the gravitational potential is mgh, right? The gravitational force times the height. And what people have also told you is, but it doesn't really matter how you define the height compared to what, because we can only measure energy differences. We can only measure the difference between one energy and another. In general relativity, that is no longer true. The absolute value of the energy is a measurable quantity, and it is the cosmological constant. Basically, the statement is that the reference for which you should compare all other energy is this cosmological constant. If I take out everything, this is the potential energy of the universe. So this is what I mean when I talk about dark energy. And if you have just a cosmological constant, it would cause an expansion of the universe, in fact, an accelerated expansion. And from this amazing depiction that I gave you here, you can see that a large cosmological constant would cause an even faster expansion of the universe. The bigger the cosmological constant is, or the more dark energy you have, the faster the universe is going to expand. Now, the cosmological constant is actually a very simple one once we understand what cosmological constants are. It is the simple fact that when we measure this object, this cosmological constant, what we find is something that is very small, 120 orders of magnitude smaller than what we would predict, okay? It is not for nothing that this is called the worst prediction of particle physics. And this fact that the cosmological constant is so small is equivalent to saying that our universe is expanding much, much slower than we expected it to expand. Okay, so this is what it means when we talk about the cosmological constant problem. It's simply the fact that this thing is expanding so slow. However, 120 orders of magnitude are a bit hard to imagine. A more accurate prediction would have been to compare the density of water to the density of a black hole. In fact, this is around 40 orders of magnitude more accurate than the cosmological constant error. 120 orders of magnitude is really an enormous difference that is hard to comprehend. And it's really, really a bad prediction. And you might ask yourself, okay, if it's so bad, can we really solve it? And indeed, this is the depiction of you thinking that, and indeed we can. And the first step that people usually take when they try to solve this problem is positing that the universe is very big. Now, you might think that the universe is big, but we're going to talk about the universe that is much, much bigger. And basically, you would have a landscape of universes, a bunch of universes sitting right next to each other, where the cosmological constant is some absolute value, some reference value that is the actual kind of complete cosmological constant, plus some random number, and that random number will slightly change between different locations in the universe. Now, this is also important to distinct, by the way, this landscape of universes from what Marvel would think of as parallel universes, or what the many worlds theory, which is more scientific than Marvel to an extent. No, it is more scientific. I'm kidding. Which is more scientific than Marvel, what that posits as parallel universe, because in this case, these universes really are kind of sitting next to each other. You don't need to, invent some weird way to work between them. You just need to go for a very, very long time, in fact, probably an infinite amount of time, in order to cross from one universe to another. And in each of these universes, the only difference between them is just that this cosmological constant is slightly changing. And we often would consider these either separate universes or patches inside a larger universe, just like a blanket made of patches. These are patches that each of them is like a separate universe with its own cosmological constant. So this is the first step. And why is this helpful? Because if the cosmological constant is different in different locations, then while most places would have a large cosmological constant, as we predicted, perchance, just because you have a lot of these different regions, one of them will have a very small one. And this one is just where we are. Okay, so if you just, instead of having one random number, if you have 10 to the 120 of them, then obviously one of them is going to be a very small number. So this is kind of how you try to create a universe that would have a very small cosmological constant. But this is not the end. And the reason is that you still need to explain why we are specifically here. If you're telling me that most universes have this random number and it's bigger, why should we be in the one that is very, very small? Why is this our observable universe rather than any other location? And the way we try to address this issue is using something called the anthropic principle. So basically, now we can explain why there would be regions where the universe is expanding so slowly. But the question is why we would be in such regions. And we call this one of the main, or perhaps the only solution that people like for this problem is using the anthropic principle. So when I talk about the anthropic principle, I want to make a very important distinction. The anthropic principle tells you that in some sense, the existence of humanity is important. It is a non-trivial observation. Humans existing is not necessarily an easy occurrence to just happen randomly. However, I'm not going to tell you that we have souls or that we are more than molecules and atoms. This is not what I'm trying to convince you. This is not a new agey concept here. This is simply the fact that the existence of humanity is a non-trivial observation. There are different levels of extreme. There is a strong anthropic principle, the weak one, but the basic principle is that humanity is it's not trivial for humanity to exist, but it doesn't mean that we are in any way magical or the rules of physics should care about us. Okay, so what does it actually mean that we are important in this case? Well, if you just have a cosmological constant, you can form chemistry. But if you have a very large cosmological constant, the universe is expanding so fast that you could tear apart atoms, so you no longer would have protons and electrons next to each other. And even if you reduce this cosmological constant further and further, you might start to see atoms and molecules, but you will not see galaxies until the cosmological constant is very, very small. You don't have galaxies and stars and heavy elements, which are what necessary to form us. So if a very large cosmological constant is, something that does not allow for the formation of chemistry and life as we understand it, obviously, we're not going to measure a very large cosmological constant because we cannot be here. right? We cannot form if it's so big. So while all of these universes with a large cosmological constant are just sitting out there doing their thing, okay, they're not going to have life to measure their cosmological constant. Only the very, very rare locations, the very rare patches or universes with a small cosmological constant can form stars in chemistry and can have humans to actually measure this observable. So that is what the anthropic principle tells us, that all of these other regions, while they do exist in time and space, they don't have humans to measure them. And that's why, obviously, any human that measures something will measure this very, very rare and unique observable, this very small cosmological constant, or the very small expansion of a universe. This might seem like the problem is solved and we can, go back to our lives and do some other thing. But it's only because I haven't mentioned the existential horror that is called Boltzmann brains. So Boltzmann brains are a very, very weird thing that many people just like to not think about, but they are completely scientific. They are a prediction of quantum field theory, and they are a major problem when you try to solve the cosmological constant problem with the anthropic principle. So what are they? To understand that, we need to go back to a statement I made earlier, which is that in the quantum vacuum, particles are always created and destroyed. Okay, this is something that happens all the time. It's going to happen to electrons and positrons, and it can even happen to more complicated molecules. The more complicated the molecule, the more rare the occurrence of the particle being created and destroyed. But I also told you that we are, in the end, just atoms and molecules. So wouldn't that mean that an entire brain, an anti-brain, which is just a brain made of antimatter in this case, can be formed and subsequently destroyed? Now, this seems already horrifying that you have brains that exist for mere moments and immediately get destroyed, but this is not the actual horrifying part. The problem is that, this is a thing that only happens once in a very long time, so you don't need to necessarily worry about it too much, because it only happens once in 10 to the 10 to the 10 to the 10 billions of years. However, if you have an infinite amount of time, if your universe just is going to keep on keeping on, which current anthropic solutions or just most theories predict that it should, the universe should just keep on existing, why not? Then this would happen in an infinite amount of time. Because no matter how unlikely a process is, if there's a finite probability and an infinite amount of time, then it will happen an infinite amount of times, right? So anything that has a finite probability to happen, if you wait long enough, it will happen once. If you wait even longer, it will happen twice. And if you wait an infinite amount of time, it will happen an infinite amount of times. So this is the thing that happens an infinite amount of times. So the next question is, you might think that you are right now thinking that this is an amazing talk. However, you don't know that in 1 millisecond or 1 nanosecond, you will actually exist to keep on listening to this talk. And the reason is, if you are a Boltzmann brain, that you are just a momentary fluctuation of the vacuum, doomed to return from whence you came. Basically, you might think that, oh, this is a very rare occurrence, so it's very unlikely, but I already told you that this happens an infinite amount of times. The amount of time your parents have met and were able to produce you, okay, or the sun has existed, etc., is basically one, okay? You only exist for real once. While these Boltzmann brains that are thinking the exact same thoughts that you are currently thinking would happen an infinite amount of times, and all of the memories that you think you have are just random fluctuations of the vacuum as well. Though, of course, if this is true, that means that any single thing I'm telling you is not based on actual evidence, because none of the things that I think I saw actually happened. These are just random fluctuations of the vacuum. Your brain is not real, neither am I, and therefore none of this is real. So if this evidence doesn't exist, we shouldn't believe in Boltzmann brains, because we've never seen any evidence for quantum field theory. But if we shouldn't believe in Boltzmann brains, then that means we're real again. But if we're real again, we should believe in Boltzmann brains again. So this is a bit of a confounding thing. And like I said, most people just like to kind of forget about it. And the problem is that if you just forget about it, you're just sweeping a problem under the rug, which is, if you try to just, quote unquote, use the anthropic principle to solve the cosmological constant problem, you suffer from this measure problem, which is trying to define probabilities over an infinite amount of time, okay, for things that happen once, right? Like our existence happens once. And there are many attempts to solve this. I think no one is really convinced that anyone has ever managed to solve this problem, because the basic premise is really simple. It's just, if you have something that can happen and you wait an infinite amount of time, it will happen an infinite amount of times. And so basically, if you try to have this infinite universes that exist forever, you just always suffer from this major problem, which is, why do you think that you are the real you versus a random fluctuation of the vacuum? This is somewhat similar to something people call the doomsday argument, which kind of try to claim that we are likely to be amongst the last humans ever left, because if you're a randomly distributed human, because humans, grow exponentially, you should be much more later. You should exist, if you're randomly distributed, you should be choosing a later time. And here in this case, it's just a statement that if we exist only once and you wait an infinite amount of time, you are much more likely to be a thing that would happen an infinite amount of times. And many people, many people try to solve this by kind of trying to get rid of the infinities in many different ways. But I think the easiest thing is go back to the drawing board and understand that to get rid of infinities, the only real way to do it is that the universe must be destroyed. If there's no more infinite time, if the universe no longer lasts forever, then we don't need to worry about not being able to compute these very unlikely scenarios that would still happen. Of course, I want to be very clear. This is not me actively participating in the destruction of the universe. It's just a statement that the universe needs to be destroyed for us to be able to make any sense of any computation we ever make, of any prediction that we have, of any prior that we have if we're thinking in a Bayesian way. Okay. Though, of course, again, it's not really an active participation part. On our end, it's just the understanding that we need to have some mechanism for the universe to have a finite lifetime. And this is kind of the end of the introduction, basically. And now I'm going to talk about the actual new work that we introduced. All of the things I told you are basically known. And this is coming from a paper called Crunching Away the Cosmological Constant Problem, or Dynamical Selection of a Small Lambda, where lambda is just the letter we use for the cosmological constant. And these are the people who wrote the paper with me. There's me, there's Csaba Csáky from Cornell, and there's Michael Geller and Tomer Volansky from Tel Aviv University. And now we can actually discuss what we did. So, So this slide is kind of me telling you everything that I will tell you throughout this talk in, broad strokes. So this is why if you fell asleep, this is a good time to kind of wake up and recouple. So again, the cosmological constant, the thing we try to solve, you can phrase it in three different ways, basically. Why is the universe expanding so slowly? Or why is there so little dark energy? Or why is the cosmological constant so small? These are three equivalent questions. And if you compare our new model to the ye old anthropic solution, first of all, we have the same thing. We both have different regions of space that would expand at different rates. We would have kind of this landscape of solutions, these patches with different cosmological constants. Then in our solution, if you expand too fast, you would die very early on. The universe would disappear. And in the anthropic solution, regions that expand very fast simply have nothing interesting going on in them. And in our model, basically, if you wait a few billions of years, the only regions that survive are those with a small cosmological constant. While in the anthropic solution, life evolves only if you have a very small cosmological constant. And therefore, in both scenarios, if you measure the cosmological constant today, you will have to measure a very small one, either because there is simply nowhere that currently exists with a large cosmological constant, or because your life cannot be formed if you have a large cosmological constant. So these different approaches are similar, but different. And the anthropic, we do not suffer from this problem of the measure problem or the eternal inflation of the universe that the anthropic solution usually suffers from. So to kind of try to draw this, I'm going to have a much better animation later, but just to sort of give you the picture as fast as I can, you have all of these universes with different cosmological constants, and then you wait a bit, and everywhere that has a large one disappear. You wait a bit more, everyone that have a medium cosmological constant disappear, and you wait a bit more, and in the end, the slides do not listen to me. In the end, only regions with a very small cosmological constant would have galaxies formed in them, and the other regions no longer exist at this point, and we are simply here. So now let me give you quite a few more details, but this is kind of the broad strokes. The actual thing that we introduce, if we talk about the physics and not just me talking in the air, is we introduce three new sectors to the cosmology. Basically, three new sector is kind of an ill-defined term. okay? But it's basically kind of electromagnetism. You can call a sector of particle physics. The strong force would be another sector, maybe. So these sectors are kind of new fields, new particles that we introduce to the model in order to try to solve this problem. And the three sectors are first the inflationary sector, then what we call the scanning sector, and then the crunching sector. So what is an inflationary sector? Basically 13.8 billion years ago, which is what most people think of as the apparent singularity of the Big Bang, your universe had a lot of dark energy. Okay, and this dark energy is coming from this new sector, these new fields. So in this case, up to a small lie that I'm telling you, in this point in time, indeed, the universe has the cosmological constant that particle physicists predict. Now, the more dark energy you have, again, the faster you expand. So very quickly, if you start out with two particles that are close to each other, they will be torn apart and the universe will become very diluted, very cold. There's nothing going to be in there, right? And that's not good because our universe has things in it. And this is why this inflationary period, the period of extremely fast expansion, is followed by a period where some of the dark energy decays. And this decays to regular old particles that we know and love, protons, nucleons, electrons, whatever you want. And therefore, you move from this highly diluted universe to a universe that is hot and full of particles. Now, this expansion or inflation and decay, also known as reheating, are actually very common ingredients. We did not invent them, of solving a problem called the horizon problem. I'm not going to explain that because it's a completely different issue and I don't want to get scattered even further. But they're not something we invented. They are very common. I would suspect that many cosmologists consider these to be kind of a known fact because we don't really have any other good solution to the horizon problem. So this is not a new thing, but it's just a statement that in the early universe, you have a lot of dark energy, and some of the dark energy then decays to reheat the universe. So this is the inflationary sector. What about the scanning sector? Basically, you have a group of fields that can be sorted out in many, many different ways. So they can be like that, they can be like that, they can have many, many different ways in which you can sort them out, and that would change between different locations. So if you start out with a universe that is basically homogeneous, small random fluctuations would cause different locations to have these fields sorted out in different ways. And when they sort out in different ways, that would cause slightly different cosmological constant. Okay, the different sortings of these fields lead to different cosmological constants. And that is exactly what gives me the patches I showed you earlier. These different regions that have different cosmological constants are going to come from the scanning sector that is, being scanned, quote unquote, right? You kind of scan these different sortings out in the early universe. Now, scanning sectors are also a very common thing in any anthropic solution to the cosmological problem. This is also not a thing we invented. And it has existed in the literature. So what did we actually do? These are all things that existed. The thing that we added is the crunching sector. So the crunching sector is a very, very weird gas that would surround us all. And when I say very weird, I mean it is not made of any particles. It is not made of even particles as we conceive of them. Okay, it is what we call a thermal conformal field theory. However, it is very useful to think of it as a gas because it is, in some sense, a bosonic gas. So it is a gas, but a very, very weird one. And it has no it has no smell or taste, and it is fully transparent. Light would not interact with it, basically. So it's just all around us and we don't even notice it. And basically the universe cools down due to its expansion, right? Because I told you, as you might remember the ideal gas law, where it's like PV equals nRT or NKRT, wherever you define these random variables, whatever it is. Basically, it just tells you that as the volume expands, as the universe expands, this gas is going to cool down. And once it cools down enough, it would go through a phase transition. And for those who are familiar with the term, it's actually a supercooled phase transition, but I don't want to get too much into it. Now, these supercooled sectors have existed in the past. People have thought of them, but no one really have used this to solve this cosmological constant problem. And this combination of things to solve this giant problem is the main novelty of what we did, trying to use this thing that was completely separated from this problem before to solve this major problem. So, as I mentioned earlier, you have this gas that is everywhere. The universe is expanding, therefore the gas is expanding, and therefore the gas is cooling. And at some point, the gas will liquefy or go through a phase transition. And the gas gives you a contribution to the cosmological constant, while the liquid gives you a negative contribution to the cosmological constant. Okay, this is very similar to the reason why you have latent heat. I would even say probably exactly the same reason. Like when you cool down water, then when you heat up ice, you have latent heat there. Basically, different phases of this gas have different latent heat, and once the gas liquefies, it has a very, very negative, quote unquote, reference energy for potential energies. So that's why when the gas liquefies, it gives you a negative cosmological constant. I already told you that a positive cosmological constant causes an expansion of the universe. So you can extrapolate that a negative cosmological constant would cause a shrinking of the universe and an eventual collapse. So when the gas is there, it slightly contributes to the expansion of the universe. But once it goes through the phase transition, very quickly the universe shrinks and at some point disappears. In this amazing animation that I spent way too much time on and did not actually end up being very pretty, I'm going to kind of show you the full details of what is the history of the universe. So we start out with inflation, where simply the whole universe is expanding. It is quite homogeneous. But then each patch gets a slightly different cosmological constant due to random changes. They're all going to have slightly different cosmological constant. And our thermometer is blue, which means the whole universe is very cold. But then you have reheating, where the dark energy decays to heat up the universe. So all cosmological constants are going to become smaller. And all the universes or different patches of the universe are very hot now. And now, if you have a very large cosmological constant, your universe is going to cool down very fast. So regions that have a very large cosmological constant are going to expand very fast. And once you reach a critical temperature, this gas is going to become liquid and the universe disappears. And universes that have a medium cosmological constant would cool down or expand slower. And therefore, they would still be above this temperature of liquefaction, the temperature of the phase transition. However, even them, as the universe expands, will at some point go through the phase transition and subsequently be destroyed. Until 13.8 gigayears after the apparent singularity of the Big Bang, only the regions of the universe with a very small cosmological constant would still be warm enough to survive. And basically, if you wait a few billions of years, life can evolve there. And if you wait a bit more, you would have the stock. However, even in our patch, at some point, the universe is going to cool down enough for the phase transition to occur, and then our own universe would also disappear. Now, I will say the actual prediction of when should this happen is it's a stochastic process. It's a random process. It can happen anytime in the next, I think, 15 billion years was the number that we had. But at some point, it should happen. And it is such a complete and utter destruction of the universe that when the universe crunches, as far as we understand general relativity, not even time can survive. So it's not only space that kind of disappears. It's not like, I don't know, the Earth being destroyed by supernova or something. There's not even any sense to saying that anything happens after this, because the universe, time and space, they are all going to simply end within a singularity. So this is kind of a very complete and utter destruction of anything as we understand it. Though again, you probably have a few billions of years, so I wouldn't sell all your belongings yet or leave your partners or whatever. But aside from this kind of prophecy of doom that can happen anytime in the next 10 billion years, we do have slightly more, let's say, falsifiable predictions, things that we can discover without dying, which are, first of all, we have light from the very early universe. And while this gas does not interact with light directly, it can gravitationally affect light. So you can measure the gravitational pull of this gas on light from the early universe. Okay, we call this light from the early universe the CMB, the cosmic microwave background radiation. And we have measurements of that. Though I think that in the scope of what humanity seems to be planning on building in the next couple of dozens of years, we probably won't be able to fully exclude this using this kind of measurement. However, we can discover it using this kind of measurement. A more sharper prediction is that if you use a collider, then you should be able to produce some of the fields of the new sectors that we are introducing. Basically, the LHC is kind of limiting whether we should expect to see these fields there or no. But future colliders that we expect to be built probably will take a couple dozens of years, but will seemingly will happen in CERN, the FCC, the Future Circular Collider. We do expect them to be able to probe the theory and basically completely show whether it's real or not. So these are not just me talking in the air and claiming things and drawing on the board. We do have sharp predictions, and this theory could be shown to be true or not true within the next 20 or 30 years. I don't remember exactly the plans of building new colliders. And for anyone who fell asleep or is looking at this on YouTube and wants a too long didn't read summary, basically, I will repeat everything I told you right before we're going to end very soon. Basically, dark energy is the main component of our universe and is responsible for its accelerated expansion. And particle physicists have a prediction for what it should be, and that prediction is very wrong. The universe should be expanding much faster than it actually is, which is equivalent to saying that it should have a much larger cosmological constant or a lot more dark energy. And my personal research that I presented to you offers a new model where if you have a large cosmological constant, you would quickly disappear. So in the early universe, these places existed, but by now they no longer are there. So only regions with a small cosmological constant, such as our observable universe, can survive for 13 gigayears, which explains why the cosmological constant is so very small. And the last important thing is that this is a physics model. This is not a religious model. We do have actual predictions, sharp predictions that can be looked for within within future detectors. And there are, I think, other avenues of research that I'm currently exploring and can be explored that are based on this. And people have tried to solve other problems in the standard model by doing basically the same thing, where you kind of kill the regions you don't want to have. There is a problem called the hierarchy problem about the mass of the Higgs particle. So people have wrote down models where basically any region that has the thing we don't observe basically disappear early on until all you remain is our universe. So this kind of, I would say, general thought process of destroying regions by having a negative cosmological constant is a very useful concept that has far-reaching consequences. And if you want to know more, you can read the actual paper. It's available online. This is its title: Crunching Away the Cosmological Constant Problem, Dynamical Selection of a Small Lambda. And you might want to do it quick, because at any moment, the universe could go poof. So thank you very much for listening. And as you can see, I used, again, the AI to give me a very nice drawing of Boltzmann brains, the universe, satellites, and patches of universes. That's it.
Thank you very much for that talk. That was great. So at this point, we will take questions from the audience. Feel free to, I guess, raise your hand or type your question into the chat. You can read it out loud, or you can raise your hand and I'll just unmute you. Oh, and I should also say I put the link one more time into the chat to sign in. So if we can get as many people to sign in as possible, that would help us out a lot, including the speaker and the facilitator. Yeah.
Okay. So let me click this and just because I know chats disappear.
I guess I have a quick question that's unrelated to most of your talk, but what software did you use to generate your AI images?
It's called AI Playground. It's a very nice program. I highly recommend. It was much more. Also, the other advantage of it compared to like DALL-E and what's it called, Bing Creator, is that you actually own the rights for the images fully, like commercially. So you can create your own images and then you own them. It's a very nice program.
We have a question from Eli. Does the solution work if there's only a single universe, or does it require a patchwork of universes?
So I would say Okay, so the answer is this solution only really works if you have the patchwork of universes. And the reason is that if you only have one universe, it would have a very large cosmological constant and immediately get destroyed. Okay, there's kind of nothing that tells you that humanity should exist, right? Or that anything interesting should happen in the universe. There's nothing prohibiting you from that. So that's why you need this patchwork of universes. However, I will also say that when we say patchwork of universes, it's important to understand that actually, in the end, there's only one real universe. It's just easier to comprehend these as separate universes, but they are all in the end part of a single system of mathematical rules that just have a different cosmological constant, and therefore it is easier to conceptualize them as separate universes, but they are in the end part of one big universe. And to Taylor, that is asking whether the math is pointing us towards these patches of universes, or is this more a method of explaining results we don't understand? The answer is that I also see your question, Elia. I will answer it in a second. I mean, it's fine either, put it anyway, in either location. But sorry, so to Taylor, the answer is, it is very easy, okay, if you try to build new theories beyond the standard model, beyond what we understand. It is a very natural occurrence that the math points us that you would have these patchwork of universes. The different universes would have different cosmological constants. However, the amount, quote unquote, of universes that you would naively have is not that big. So the way that when we construct kind of new models, the math usually does point us towards having multiple patches of different cosmological constants, but to actually have a vast array of like very, very, slightly different cosmological constants, to have what we call a scanning sector, where you really have, a very fine difference between the cosmological constant, that is less natural. That is something that, we are kind of adding there and does not necessarily need to exist. And it's possible that, there are other solutions, that would not require you to have this patchwork of universes. There are kind of attempts to have, let's say, like a cyclic universe, where you sort of, instead of having these universes different in space, you sort of have one universe, but then it gets kind of destroyed, and then it gets created again. And every time it gets destroyed and created, you kind of, quote unquote, sample a different patch. So there are kind of different ways that you can get. However, I mean, to answer your question, I think the math is pointing us a bit in this direction, but perhaps not all the way there. It's possible that, the actual solution to the cosmological constant does not actually require this. It's just there hasn't been any real way to do this within a single universe that in no way actually samples these values. And to Elliot's question, you're about the expansion of the gas causing the universe to expand, or the other way around. The answer is it's both. The gas is causing the universe to expand, while the universe is expanding, causing the gas to expand as well. However, the majority of the causality is the universe is expanding, and therefore the gas is expanding. The effect of the gas on the universe is much more minor than the effect of the universe on the gas. That is until the gas becomes liquid. And once the gas becomes liquid, it becomes the most important thing in the universe. And by the way, when I say liquid, I really mean goes through a phase transition. And once it liquefies or goes through the phase transition, it becomes the most important thing driving the expansion, or more honestly, the collapse of the universe. So the causal relationship is both ways, though mostly universe causing gas. But once you become liquid, the game changes and it goes the other way around.
There's another question in the chat from Taylor. Is there a way that we can study this dark phase transition?
So, okay. The answer is, it's complicated. Basically, the main way to really study it would be to see its effect on the early universe, to basically see kind of, so once you go through the phase transition, you basically die very quickly. Whether or not we can protect ourselves from this death is a different question. Probably not. The amount of time it takes for this phase transition to occur is basically faster than we can form a thought. So by the time this starts, when we can see it, we're already dead, basically. But to more broadly study it without it actually happening, the answer is kinda yes. It would require a very, very good collider. You would need a very large collider that would basically produce the particles that are responsible to the phase transition, kind of the particles that are kind of being produced when this decay happens, or whatever kind of the new fields that are involved. You could try to study them using a very strong collider. You can obviously study it theoretically. You can run down more accurate simulations, though at least for us, we couldn't think of any other way other than to really study the phase transition, other than really produce the fields that are responsible for it in a collider. Or you could see the gas without the phase transition by measuring very accurately light from the early universe. These are the two main observables that we could think of, but there might be more. There's nothing kind of telling you that there shouldn't be any more predictions. These are just the things that we could think about. And I will say, if we talk about theoretically study them, that is a very active field of studying supercooled phase transitions and bubble formation, which is how these phase transitions occur, and these rates of occurrences. So it is an active field in theory. So Elliot's question is, if the crunch happens, is it only our universe gets destroyed, the other universes are not affected? The answer is that it's actually, once the crunch starts to happen, there's what we call a bubble, or a spherical kind of, we call it a bubble just because, when you heat up water, right, bubbles start to form of the other phase, of the gas phase. So basically, once this phase kind of appears, it's very similar to a book called Ice 9 by Kurt Vonnegut. What happens is, basically, this phase, the rest of the universe finds out that you can do this phase transition, and this bubble starts to expand and basically occupy a larger and larger volume. Because these universes are so massive, the answer is that basically the specific universe where the phase transition starts to occur will be destroyed by a single bubble. And by the time it reaches another universe, it is far more likely for this other universe to already have its own bubbles being formed. So the process of kind of fully destroying these universes is kind of something that really occurs over time, but time becomes a very complicated quantity when we talk about crunching regions, because time ends, basically. So the answer is, it's a bit of a complicated answer, and it really requires a more careful calculation, I would say, to really say for sure. But the basic answer is, the destruction becomes kind of, overtakes other regions. But if you have your own large cosmological constant, you will already be destroyed. So if you have a very small cosmological constant, at some point, you could, in theory, be destroyed by the next door universe. However, in practice, because of how space-time works, by the time this happens, your universe will also be destroyed. So it's kind of, I'm trying to answer this without going too much into the Friedman, Roberts, and Walker metric, which kind of tells you how time works in different locations. But I'm not sure if I'm really landing it in a way that's clear. The basic statement is, you're right that they get destroyed, but because time is a relative quantity, how much time it takes for a universe to be destroyed kind of changes between a small cosmological constant universe and a big one. And in addition, the big ones will also form their own destruction either way. I hope this actually answers you in a way that's somewhat clear. So you're asking if the patchwork of universes is infinite. The answer is kinda yes. But it doesn't have to be. There is a thing called the curvature of the universe that can you can easily turn it on, basically, and cause this patchwork of universe to be not really infinite. But fundamentally, we usually just conceive of it as an infinite thing. It doesn't really have to be. It's not really a crucial component. We just don't really want to deal with finite curvature, which would kind of make it end. But turning it on really shouldn't change any conclusion. So while technically it is infinite, it is also kind of not really. You can easily make it not infinite without working too hard.
Okay, great. I'm gonna
Yes.
end the formal lecture here. If Itai, if you're available to stay on a little bit longer to answer
Yeah,
further
I can stay.
questions, that'd be great. But I want to thank you for speaking, and let's thank our speaker one more time. Sad applause by
Thank you.
myself. But and yes, we'll continue. We'll have another lecture next week, and we assume that it'll be back in the hybrid format. So we'll have an in-person component as well as a Zoom component. So yeah, thank you everybody for attending.